Recording has started. All right, there we go. John,
Hey,
welcome aboard.
Thank you. Let me start off with a little bit of this. Maybe this is important, you know. Everyone may recognize this if you are a good nerd. That is from Lord of the Rings, and that is what this moment is about. You know, we're in this very disruptive moment of artificial intelligence. And I guess my goal here is to satisfy these constraints that I've been given. Let me sort of go through that list 1 second here. Let's see, kind of. Okay, let me open up the main window over here. Let's make a zoom in. Okay, so we got over here, big picture of AI order. We got what the heck's a Copilot stack? We have, you know, if you're a veteran coder, what does this have to do with me? We have the custom Copilot recipe, and we have the difference between the Azure OpenAI SDK and Semantic Kernel. I will be taking requests in the chat channel. I am like a gamer, so go ahead and type over here. Okay, and if you want to ask any question to stop me, remember I'm not a video. I believe I am alive. Okay, here we go. Now, first up, I want to start off with the big picture of AI. And then I want to kind of dig into some practical things you can know about building these copilots, which may not be obvious if you're just thinking about how to code them. And I think this is a terrific, this chat for the NYC example of you can deploy these things and you can deploy them so they're relatively safe. But, you know, how do you do them in a way that's like best in class? Surprise, all of it is not a technology stack question. There's a pretty big UX question involved with that. So we're going to go into that as well. And I'm going to try to differentiate semantic kernel from other things you'll be hearing out there. Okay, so how's that sound? As a menu, can I get a thumbs up or something in the chat channel so I know someone is out there? There we go. Oh, I see it. I see it. I see people alive. There we go. Good, 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 good. Thank you. Thank you, Kip, Pritesh. Thank you, Craig. Lee. Got it. Okay, here we go. We're going. Here we go. We're going. Let's come follow me. Come follow me. Here we go. Okay, so first off, let's talk about the big picture of AI. So it's pretty important that we have folks who have been coding for a while. So let's try to draw this backwards. We got 2023. And then let's go to like 2010. And then let's go to the year 2000. And then let's go to the year 1990. And let's go to the year 1980. And I can keep going back because computers are pretty old. But the reality is that when people are surprised by this moment, like, whoa, where does this AI thing come from? They may be missing the context of how technology does this to us. So first off, I want to go back to the 80s. We mentioned this computer. It was called the TRS-80, lovingly called the Trash 80 computer. And it wasn't a piece of trash, mind you, but it was lovingly described that way. This computer, not so powerful, you know? But what happened in this era is because of Moore's law's doubling effect. Mind you, Moore's law, the idea that computing power or storage power, whatever the computing era, doubles every roughly 12 to 18 months. A what happened is that the trash 80 was okay, but the next version wasn't just like 5% better. It was like twice as good. And that twice as goodness kept growing to the point of, as we all know, I mean, like, look at this thing in our pocket nowadays. It's like so powerful because of doubling effect. So this is Moore's law effect. And the reality is that I never truly respected Moore's law. I mean, there are people here who are like, oh yeah, I'm really into Moore's law. I was never really into Moore's law. I really liked it as an idea, but never really felt it until the following moment. Those of you in computing know that it's pretty hard to explain to someone how computing works. You're like, well, there's a processor, there's memory, the internet, whatever kind of thing. You try to explain technology, computer technology to someone, it's pretty hard. And so I went on a journey to write a book called How to Speak Machine. And How to Speak Machine is a way to teach anyone how to speak machine. It's a way to teach anyone like Spanish level 1 computer science, because it was meant to kind of help people speak un poco computer science. And in my journey to create this, I discovered a wonderful British riddle that really accurately explains Moore's law. So we're gonna do a little interactive thing in the chat session. So everyone who likes to win contests, get ready. Okay, so here we go. So there's an old British riddle. There's an old British riddle, and this is some trees over here, a little house over here, a little cute little sort of house. And there's a big pond, and the pond has a bunch of lily pads on it. Those of you who go, wait, you're like from the part of the country where you probably go camping. Some of you go camping once in a while, so you go camping. So there's a beautiful pond, and then the pond is small. It has, yeah, Lee does that, and the pond has lily pads on it. So, anyways, a biologist lives over here in this house over here, and what she does is she wants to run a scientific experiment. And it goes like this. She like gets rid of all the lily pads and she plants a certain kind of lily pad that doubles overnight. So it's like on day number 1, there's 1 lily pad. And then on day 2, there is 1 plus 1 is 2, right? 2 lily pads, that's day 2. And then day 3, 2 doubles, 2 times 2 is 4, right? And then on day 4, it doubles and 4 becomes 8, right? Okay, so the way the British riddle goes is on day 30, on day 30, the pond is completely covered with lily pads. On what day is it half full? Okay, answer in the chat. Answer in the chat. What day is that pond half full? Day 30 is full. What day is it half full? Okay. Lee says 29. Steve says 29. David says 29. Jason says 29. I will tell you that if I answered this like 5 years, 8 years ago, I would have said 15. I'm not smart as Jason and David and Steve believe. Clearly, you've been thinking about this. I didn't think about it. I was like, well, it's got to be day 15 because half the 30 is 15. Half the pond is 15 days, right? But it's wrong. Because on day 29, the pond was half full. And half full just becomes whole full in 1 day. So what is the lesson from this example? Well, it turns out that in the first days of like this doubling, you just don't notice it, doesn't matter. It's so tiny. But then in later stages, in later days, the doubling is significant. And not only that, now think about the person who's thinking about like day 29, it was half full, and then day 30, it's whole full. But then day 31, what's happened is you got like two ponds. This thing is like flowing over, right? And then on the day 32, it's now like four ponds, like a lake. And so you can imagine the ocean gets filled rather quickly with this. Okay, so why is that important? It's important because when we think about this history of computing that began in post-World War II technology, etc. Let's put it at 1970-ish. But what happens is the doubling has been very unusual. It's like it's unnatural to us humans, but this is very native to the computing world. And in the computing world, this doubling has occurred. Now let's talk about AI for a second. So can I get a sign of hands of gestures of those people who worked in AI in the 80s or 90s? Raise your hand. 80s or 90s people. AI? Anyone was near AI? No near AI people out there? Okay, so I was one of these people working on AI in the 80s and 90s. And it became unpopular very quickly because it didn't work. Why didn't it work? And by the way, for those of you who are machine learning experts, I will get to the more advanced topics, but I want to level set the knowledge in this room here. And I apologize if I am too behind, but I hope this context is useful. Okay, so the AI of this era, so-called pre-AI nuclear winter, you want to remember that most of the scientists of this era either fought in World War II or fought in the Vietnam War. When I was a professor at MIT in my early career, a lot of them were my colleagues. And so I had a sense of this history, the backdrop of these computing giants. They had all fought in war. And so they would use war analogies all the time. And AI nuclear winter was significant. It was a sort of overstatement, but it meant that the research dollars went away. Um, the reason why the research dollars went away, a variety of reasons, but there were two strains of AI. One was based on so-called symbolic computing, and the other was based on so-called neural networks. We use the letters NN. Okay. Now, these two approaches were very different. This was in the 50s. There was like a battle, a kind of AI smackdown era, basically, where the two, it was like, no, 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 we're going to do it symbolically. And like, no, 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 we're going to do it with neural networks. So the problem with the neural network people is that the processing needed to do neural network processing was prohibitive with the computing technology at the time. You could do it with analog circuitry, but it didn't scale very well. Meanwhile, with digital circuitry, it was more possible to develop symbolic computing. Good one, David. And so the symbolic computing people won, and the neural network people were like, wah, wah, it didn't work out. And you want to remember that symbolic computing was good because symbolic computing invented computer languages. If you love things like C or Lisp or Python, every language, Java, a lot of the symbolic computing, kind of compiler technology and all of that is all about symbols. And so that the AI revolution really elevated the idea of computer language design and really kind of advanced the idea of object-oriented programming before others thought of it. And so, anyways, I bow to the sort of the failed approach, which we use all the time now. If you write code, it owes its past to symbolic computing. Now, neural networks. Like, no, the neural networks were not the winning formula in the 90s or in the 2000s, but it was still kind of hanging out there. And what's important to note that in 2012, 2012, there was a landmark year where neural networks were being applied in this area that we all know as speech recognition. You know how your phone, if you have your like default phone thing turned on, it might be listening to you and you don't want it to say that to do the wrong thing. I don't say SIRI or ALEX. I'm going, when you say this thing, it's going to like, perk up and listen, right? Now, we want to remember that voice recognition was pretty horrible for the longest time. I don't know if any of you bought a voice recognition or speech recognizer or whatever in the early 2000s, but if you recall, it didn't work very well until 2012, because it was in the year 2012 that folks began realizing that this neural network-based approach was unusually capable. And not only that, it was processable, right? So remember that our computing legacy was built upon computing for symbols, you know. Um, uh, 2012, researchers realized, hey, there's this like video game GPU, this card, this graphics card that, I keep buying a new one and I keep buying a new one to make the graphics look more photorealistic. And then they were so cheap and plentiful. Hey, I wonder if I can do neural network style processing on a GPU. And GPU is a vector-based calculation like instrument. It's got all that magical way to work with large clumps of numbers. And so it turned out that the GPU world became the world where neural networks became relevant. And in 2012, speech recognition technology, which was largely incremental. There's a graph somewhere you can find in 2012. It was like it got this good, and then it got this good all of a sudden. It was like a step function, which, as you know, doesn't happen very much. That is not a Moore's law style thing. It was like it was a transition. Now, let me erase this for a second. So let's consider the following: that we're in the era. And slightly different from what David is describing, C# versus Java, where in 2012, we entered the quantum realm. Those of you who are like Marvel movies fans, the quantum realm is this movie. I don't know if it's that good, but it's like a quantum realm. It's a lot of science, a lot of visual effects. When it's got too many, I can't tell what's happening. But anyways, the quantum realm is a good word, quantum realm, because those of you who play with quantum mechanics or quantum physics know the following: that quantum physics is like a really weird kind of physics because it's quantum physics. So let's go there for a second. So everyone here who went to school in some shape or form learned Newtonian physics. Newtonian physics, of course, being like, Newton, like I don't know if this really happened, but it makes a good picture. Whoever thought of this idea was genius, that there's some kind of apple tree, and Newton's like sitting there, like, pontificating or reading, and the apple like hits his head and he's like, whoa, gravity. Oh, that's nice, David. Yeah, David. Oh, David's got some good, like, crawl, walk, run here. CPU, FPU, and GPU. So Newton, gravity. Like everyone knows gravity, right? Like if you like stick out your hand wherever you are, you drop something, right? Gravity. You can always count on that. And like all of physics, we can like use gravity as this sort of major idea in how we compute things. Quantum physics is different. Quantum physics, and this was described to me by what is her name? She's like the physicist. She was the person who, if you've ever seen the movie Contact, younger people don't know what I'm talking about, but there's a movie Contact with Jodie Foster and Matthew McConaughey. And she is the model for the character that Jodie Foster played, this like amazing theoretical physicist. But anyways, in the movie Contact, um, the idea of contacting, aliens from the outer space, it's all about a quantum leap. And the way that we understand the quantum leap, which I like a lot, is that at let's say you're at 10 to the 2, 100, that's like 100 feet up or something, and you're at 10 to the 1, you're standing on a ladder, 10 to the 0, you're on the ground. I mean, if you're up there like 100 feet, I don't recommend this, but if you have an apple and you drop it, it's gonna like hit the ground. If you're at 10 to the 1 and you're an apple and you 10 feet above, you drop it, it's gonna hit the ground. 10 to the 0, that apple is hugging the ground. Now, let's go 10 to the-1. You like just shrunk, and even if you're a tiny doll-sized person like this cup here, and you like drop the apple, it's gonna fall. But it turns out that at 10 to the-20 something, I forget this number, gravity stops working. Okay, with that gravity, where'd it go? It went away. And that is the world of quantum physics, where physics as we knew it went away. So it's an analogy to help at least all of you who are sort of new to this, or those of you who are deep in it. You're living in the quantum realm, Yeah, Lee, I'm like shocked every day. Like we're in the quantum, because computers, like the CPU to FPU to GPU, anyone who writes code is writing in the CPU world, the world of symbolic computation compiled to an architecture for processing symbols. Okay. Anyone who's coding in the GPU era just went into the quantum realm of coding. And so that's where we are today. And I don't mean to, I'm not overstating this in any shape or form. I find myself that I can get in the zone better when I'm acknowledging that. And for all those of you who are deploying things, you've discovered this. The most important thing to understand is how to connect and I like this, David, it's really good, the CPU world and the GPU world of computing, because it's better when you have both together. Because the CPU world, we know how to like make stuff work to like 99.99% reliability. Like we worked hard these decades to get that kind of reliability statistic, right? This is very deterministic, right? 99.999 or whatever you're at. It's over 90. When you're over here in the GPU world, good luck getting 99.9999. It's not designed that way. It's designed in a completely different way. It is like the quantum realm. And so the challenge of developers is to be able to combine these to combine the best of these two worlds together, and to design the clutch to connect the two together. So that was a long, grandiose way of explaining what the heck semantic kernel. Semantic kernel. So semantic kernel, this is the official semantic kernel T-shirt that I designed, is about this capability of a developer to live between, I guess we would call it like native regular code, symbolic code, syntactic code, to the what my boss Sam Scalacci, the creator of Google Docs, he's the deputy CTO. Sam, whoa, mind blowing. He calls this world the semantic world. So the semantic computing world is fundamentally different than the syntactic computing world. Okay, so now let's acknowledge. So let's see. Let's get a raise of hands. Of do people feel that they feel the quantum realm a little bit? Can you do you feel it? I'm not sure. It's like it's over there. So I hope you have a glass of whatever. But do you feel okay? Ritesh feeling the quantum realm. Jason's feeling the quantum realm. You got to come with me on this, folks. Here we go. Okay, good. Thank you for coming on the journey. You're in. Oh, David, sorry, David. Okay, David's still living CPU, FPU. I don't know, GPU. We should always have people who are curious. Okay, more like exponential world. Oh, that's a different. Okay, well, I don't know. We can argue exponential versus quantum, but anyways, I live quantum world to live this dream of like, wow, it's so different. When it's so different, we become a different person. Okay. Yeah. Okay. So combining these two worlds is important. Now, what is rule number one? If you acknowledge this, let's use a super duper exponential or a quantum shift. The first thing you need to do is you need to change the way you think about how you as a native code developer looks at this stuff. So let's say I'm living in the CPU world and I'm used to like getting a little, if you're not a machine learning person, you're like, whoa, I gotta like, figure out how to build a model, right? That's the whole machine learning, deep learning, AKA AI world stuff. You're gonna build a model. When you build a model, it takes time. I mean, like you can't do it like in a few minutes or a few hours because you need a lot of data. You need a lot of data to create the model. So most people have this mentality that AI is expensive and it takes a lot of time. And I think in the example of the My City chatbot, like, creating the model to make that work would have been prohibitive. I mean, it would have been too expensive. It would take too long to make it. But what happens in this new world is uh, you no longer have to produce the model. You can now consume the model. So let's hands up for a second here. Left hand, consume the model. Right hand, produce the model. Produce the model is what everyone is used to doing. So David's got that. It's like everyone's like, oh, let's do some AI, machine learning. Oh, let's go make the model. Wow, that's gonna be hard. Let's give up. And the consume the model is like, whoa, let's go use a model. Which model? Well, there's lots of models now. Does it work? And that's this error. We need to consume the model. And Semantic Kernel is a SDK to enable people to consume the model. So let's jump into that, shall we? Let's go there. So those of you who love to download repos on GitHub, you're like, no, I don't want to download another repo. No, I'm not sure about that. Well, let me tell you what can happen after you download the repo. Okay, so if you go to the Semantic Kernel repo, there is a file structure like this, like everything. And I'm going to .NET and I'm going into notebooks. And what you can do is in notebooks, there's these different notebooks, and they're using Polyglot Notebook Extension, which is so for those of you who don't know what this is, it's something a little newish, and you can go to Polyglot Notebooks and extension, you load this thing up, and suddenly you get to be able to do Jupyter style notebooks like the cool kids who do Python. Oh, it's such a glorious thing. Now, let me make this window smaller so you can see stuff. Okay, so let's go to the first notebook. Here we go. And again, this is just freshly cloned on my computer. And what we're going to do is, if you see here, this is the very first one, AI settings. And so if you have an Azure OpenAI key, you'll set this to true. That's kind of hard to come by, so you might have a regular OpenAI key. You can get a free one or put your credit card in, and it's like pennies per month kind of thing if you don't like That's like, build a new AI startup. It's easy. And then this will just, and this is the notebook, by the way, those of you who have already deployed things, there's actual examples in here, but this is for people who like never ever have touched it before. This is a very simple way to get started. So that says false, we get that. And then what's going to happen is when I run this, it pops up at the very top a dialog box that's asking me for my OpenAI key. And I have a personal key. By the way, I demo everything with my own pocket, I guess, whatever kind of thing. This is my personal key. Let's drop it in here. Okay. All right. Oh, something went wrong. The given key was not present in the directory. Let's try it again. Okay, that's it. Good. All right. Okay, so that worked. And then you want to run this if you want to reset it. Okay, that was step number 1. We're at first space, everyone. And by the way, everything stays on your computer. So what happened just now is there's this settings.json file where the key went in there. So nothing is going across the network. For those of you who care about their stuff, like me, it's not in there. Okay. So now what we're going to do is notebook, this notebook, we're going to like grab the settings file. The settings file contains the key that you just added, just mind you. And then this gets the NuGet package. And NuGet package is being updated every week. This is a week over week. So this is rapidly changing code, folks. And then you want to make a kernel. There we go. That just built the kernel. And then now I'm going to build it with the kind of a completion service, and I'll go into that in a second, but I want to just run through for here. I'm going to now run a semantic kernel plugin. And what happened here is I have something called a joke semantic function, and I give it a topic, time travel to the dinosaur age. And then it made a joke for me. Those of you who remember the riddle cups, this is like a little riddle. Why did the time traveler bring a ladder to the dinosaur age? Because he wanted to reach new heights in history. Let's change that. This is actually real code here. So let's do some so-called prompt engineering, slight overstatement, right? Invoke ASA. The topic should be coder for 30 years. There we go. Let's tell a joke about that. If this offends anybody who's been coding for 30 years, like myself, I apologize in advance. Okay. Okay, there we go. Why did a coder decide to become a stand-up comedian after 30 years? Because I realized they'd been debugging code for so long, it was time to debug people's laughter. Okay, so that's the example of the following. This is the input, the prompt, and this is the skill, the plugin. Let me show you where that is. 1 second here. Skill directory, samples, skills, and so 1 second here. Samples. Samples, skills. There we go. So what I did is I called the joke. So this is this file here is the prompt template. And if you can see here, it says write exactly one joke or humor story, make it G-rated, few. Be creative and funny, make me laugh. This is the input, and this is the style. Okay, so I want to pause for a second. For those of you who've never seen what this does, what you do in VS Code is like, thank you. Let me do that in a second here. Let me show you what happens. What you do is you in that, let me go back to notebook. Dun, dun, dun. Well, there's some very industrious people in this user group here. So you select .NET Interactive. And you get this when you have installed Polyglot notebooks. So you'll have to restart VS Code after you install it for it to work, but it's pretty cool. It's like and you get to interpret your stuff there. All right. Okay. So I want to pause because stuff happened for those. This is new. Okay. So we're going to do a little exercise here now. Let's see. I did some just a big picture. I've done Copilot stack. When I got you on a list, and I always end on time because you all have like a life to live, like we all do. Okay, so the thing to note is what I did there is there is part of me. I don't know if there's like a flowchart symbol for an AI model, but let me use the canonical database diagram, like a cylinder. Do we see a cylinder there? There is a model, and the AI model exists, but it's living in the cloud. Living in the cloud. So got to get an API key for that. I want to note that you can also run models locally. If you have a beefy GPU on your computer, you can run models locally too. But just for convenience sake, I attached to an OpenAI model in the cloud. I use my key. Okay. And the way this model works is the way that all AI models work. And it's very important to know this because at first it's a little bit confusing. Again, for those of you doing it, it's like easy. For those of you who are like, well, what's happening? There's an idea called the token window. It's called token window. So what happens, all that is basically I can send to the model, I can send a bunch of so-called tokens. And then what happens is the model will return tokens. And important to note, the model is stateless. So if you send stuff to it and it sends stuff back and you send more stuff to it, it's not going to remember that you sent anything to it. Now, why is this important? It's important because it's kind of like a game. It's a game for me, at least. Thank you. I'm going to explain that Ritesh is asking the really good question. I can send tokens and tokens come back. And it's a kind of game because if you look closely, remember those of you who were in the beginning of the conversation, we talked about, oh, my computer had 4 kilobytes of RAM. Wait, oh, my computer's got 8 kilobytes of RAM. So the token window is increasing like month over month. Someone's got like more, you can put more tokens in there. Okay. This window size is growing as the technology improves. Some models can take 32K tokens. Some can take 128K tokens. But let's explain what tokens are for the people who are untokened. Okay, let's remember again that we have the AI model, and it's in the cloud, and you can send it up to, let's say it's going to be up to 4,000 tokens. It'll only let you send 4,000. It'll let you work with 4,000 tokens, and it can return 4,000 tokens. Now, this phrase is not correct. Let me explain. So it's like talking with an alien across outer space. You've only got this much stuff you can stick inside the spaceship that goes across the transom and comes back. If you use all the tokens, it doesn't have any room to send you a message back. It doesn't empty it out. So you might use half the tokens. Let's say you put you put 2,000 tokens in there, and then what happens is that the model has a window of tokens of 2,000. It can send you back. Same way, if I use 75% of the tokens, I can only use 25% for the return response. Okay, and what the heck is a token? Token is just an example of those of you who love to parse information. It's parsing information to information into a numerical token. And so, for instance, anyone who loves to write, compilers or whatever. I don't write compilers as a hobby, but some of you clearly have stronger nerdliness than I do. No shade, all just like, love. Like the word dog, the word cat, the word animal, the word truck. Dog might be token number 1, cat might be token number 2, animal 3. So there's mappings. There's numerical mappings. Lee, I got some good nerd bribes from you. So they're just mappings. And so tokens are numerical translations of words, not correct. Okay, that's the easy way to understand it. I'm now going to give you the real answer, which we can easily find out by playing with the token. Let's see here, OpenAI token counter. Okay, there's a token counter. Can we have a token counter? OpenAI tokenizer, that's it. Ooh, this is the best thing ever, folks. So this is like, I ate my sandwich, right? It translated I ate my sandwich to 4 tokens. If you notice, the word I had a corresponding token. The word ate has, so this is 1, 2, 3, 4 tokens. Okay, now I love to eat pretzels while the world is changing around me and I don't know what to do. Okay, now look closely. I love to eat. Whoa, pretzels doesn't have a corresponding token. It broke it down into pretzels while the world is changing around me and I don't apostrophe T. So that's 24 tokens, which is not the same as the number of words. A simple example would be like the cities Tokyo, Los Angeles, Paris, Ontario is not a city. Vancouver. Oh, this is good. See how Tokyo is not like a whole token. Tokyo. Los Angeles is like, it was 2 words, but that's okay. Oh, let's go to Minneapolis. We had a Minnesota person. 1 token. Ooh, Minneapolis, you earned 1 token. Let's see here. Portsmouth. Got 1 token? Whoa, 1 token. Let's anyone have an exotic name here? I can't think of an exotic name.
How about Newark?
Newark. No. Newark is a very exotic place. Okay, but you get what I mean. So tokens don't correspond to words. Tokens sometimes break things apart. So anyways, you can sort of break things into tokens, and what happens is, again, I'm going to bastardize this math equation. It's a good way, Chip. I'm going to bastardize it a little bit because it's I think of it like, everyone remember multiplying. Wait, which way is it? Multiplying. Multiply when you multiply a vector times a matrix, it becomes a long vector, right? So vector times matrix, you get a vector. So it's kind of like, I think of this is that token window. And when you send it over, it's like doing calculation of the rest of the vector. These are your tokens. And then these are the model's result tokens. So that's why token window is important. Longer token window means you can give it longer pieces of text. A shorter one, you can now have it generate more. Now, this is where it gets interesting, folks. It gets interesting because, okay, let's see. So how many of you know Harry Potter? Anyone Harry Potter people do? Is Harry Potter popular in Atlanta, Georgia? Okay, I got Harry Potter people. I love Harry Potter books. They're thick. They're thick books. They're very thick books. They're like big books, And then when it's a big book, and let's say you had 500 pages per word, 500 words per pages. And let's say, let's sort of calculate that for a second. 500 times 500. Okay. I got, oh, wow. 500 times 500. That's actually easy for everyone here on this call. It's a bigger number, right? At some point, you cannot give the model a lot of tokens because it is a token limit. So tokens like it's like I can't take that many tokens. So a common problem with these models is you can't give it a lot of data to work with. Like I said, I want to summarize all the works of Harry Potter. You're like, wave your AI, whatever. And what happens is you're looking to the sky at your AI model, and you're saying, here you go, AI model. I'm going to give you like 5 of the Harry Potter books. I'm sorry, I don't know how many there are. 5 of the Harry Potter books. And I'm going to ask you, magical model, to go and summarize it. Why can't you do this? It's because you're exceeding the token window limitation, right? You can only put 2,000 tokens in that special processing unit. 4,000, now 16,000. This is a fundamental problem. So a lot of what you'll bump into in the code is this is the work to understand how to work with large bodies of information. Okay, so let me show you how that works. Okay, code. Okay. I'm giving a tour right now. So are people following me? Can you give me a thumbs up? I'm trying to go slowly through the canals of Venice right now. Okay, Lee, Tesh. Oh, good. Craig. Okay, good. Jason, go. Come with me down the canals. Here we go. Okay. It's meant to be like a comfortable, like evening, glass of whatever, juice or your favorite other beverage. Okay. So what I did there is you saw it happen. I was able to tell a joke about a coder for 30 years by doing the following. All I did was this was the input to this template. So let's go look again and you can change this yourself. You can go over to skills, fun skill, joke, and you see this prompt here. All it did is it stuck a 30-year coder in here. Notice that you could also provide it a style. You can provide it not just one variable, but multiple variables, which can like change the prompt. But notice how like this stuff is like fault tolerant. So it doesn't need all the variables. Okay, I want to stop there for a second. Did you check that out just now? I had a function with 2 variables and I didn't give it both variables and it didn't like, oh, you're missing the variable. I can't figure it out. It just went forward, right? It's very confident in that way, okay? But what happened is basically with the prompt template, and by the way, those of you who use LangChain, we are in the release 1. That's on our roadmap, so that isn't a secret. And this is all open source stuff. We're going to also support LangChain templates and whatever whatever kind of prompt templates exist out there. We're meant to be compatible. Okay, but all that happened is that this thing here became exactly. Let's do this actually. Let me get this. Let me drop this in the token counter. There you go. Let me drop this into here. Let me say this is zeroed out, and this says 30-year coder. Okay. So if you look at this, this is the now the question was, this is the prompt. This is the prompt, and this is the actual tokens. 99 tokens went to the model. And 99 tokens went to the model. And what happened was we gave it enough token window to be able to respond, and it gave a joke. Remember, like you got to give it what's called a max tokens. Like if my max tokens was 99, it would have like gone over there and it would have said like, oh, I don't know where to put the joke. So max tokens probably set to 200 or 300 meant that the 99 tokens went over, and then the model is able to drop in the other free token area. And don't forget that you're paying for tokens. Well, you're paying like N cents per 1,000 tokens or something like that. Depends upon which model you're using. Okay. So again, we sent things into the model. We can only send it a certain number of tokens, and we need to leave room, max tokens, to be able to get it back. Okay. Another thing. So max tokens, it falls in the category of what's called a hyperparameter. Kind of yeah, I guess so. A hyperparameter is a cool word that the young people made up sort of describe the parameters that attach to this prompt or this piece of information. Thank you, Carter. You get that. They have a hyperparameter, right? It's like the flux capacitor. So there are hyperparameters. One is called temperature. Temperature is like the easiest one. I gave it a heart mark. It's my favorite one. It's easy. It's like temperature 1.0 means, someone who comes from a warmer climate. They're like more laid back and they're like, yeah, I don't know, it's about 1 o'clock or whatever. They're just laid back. And they might make stuff up. Temperature 1.0. Temperature 0 and 0.1 means cool temperature. So it means like they're not going to make things up. So when we go to hallucination and you're dealing with hallucination, like the team that created the NYC chatbot, if they made it like temperature 1, it's going to hallucinate a lot. So temperature 0.10 means hallucinate less. Again, that's an overstatement of that is not the only way to anti-hallucinate. We'll go into that. But there's temperature. There's also a parameter called top P, and top P parameter is described in different ways. The way I learned it is top P means the number of words, the word range the response will be. High top B means it's going to use lots of words, like someone showing off their vocabulary. And low top P means they're going to stay within a vocabulary. So you can argue that a low top P is going to feel much more deterministic versus a high top P, someone's trying to like shock you with all the words. Anyways, there's a bunch of parameters here in the hyperparameter shopping aisle. But again, max tokens, temperature, kind of the foundations. And what you can now see in the actual code is over here. Let's go to .NET. There we go. Simple note. Or were we done? That over here, notebooks. This one over here. Okay. Oh, excuse me. I use this joke function. Okay. And then it's inside over here, samples, skills. Again, we're renaming skills into plugins to fit into the whole OpenAI universe. Again, this was made, designed based upon GPT-4 last year when no one knew about it. And again, this is a brainchild of Sam Scalacci. He's a special man. So here we go. Max tokens 1,000. So these are the hyperparameters, temperature. So this is where you can actually, we have this file format, so you can package the prompt, the templated prompt. So this is a templated prompt, and these are the preferred hyperparameters, and you're able to, of course, edit these in code. So for those of you who ask, like, what's the difference between this and the Azure OpenAI SDK? I would say that this is made for people who want to code across native and semantic, who love to tinker with things. And it's an open source project, so we can all learn together. Okay, so around a scale. Okay, now let's see here. So let me show you something a little more exotic. No, let's go to memory. Okay, so all right. So we talked about how if I'm trying to send Harry Potter all the way over there, it's not going to work out. It doesn't fit inside the window. So what we do is we instead use something called vector memory. Vector memory using what's called an embeddings model. Whoa, when I first learned this, I was like, really? Did you have to make that word sound so foreign? Okay, so There are two things happening in AI. One is a completion model. We used the completion model just now to complete the joke, basically. I was like, tell me a joke about, and it was like, say, tell me a joke about, and it filled in this thing. It completed that. There's another model in play called an embedding model. An embedding doesn't complete the sentence, but it is a model you can run from the cloud or locally. This is another kind of AI-ish model. And what the embedding model does is it converts any piece of text into a vector of numbers. And when it does this, when it converts it to a vector of numbers, something magical happens. Something kind of bizarre happens. What happens is that when you convert it to this embedding vector, you can do the following. So how many people here are experts at regular expressions? Raise your hand. Right, come on, go ahead. Flex it. Come on, flex your regular expression muscles. Who is a regular expression god or goddess in this group here? Come on, someone out there. Someone out there is regular expression. Thank you. It's okay. All right. Regular expression helps you like find things, right? Helps you like measure similarity with these arcane patterns, right? So with the embedding model, thank you, Steve. Now that is that not a flex or what? So with the embedding model, what happens is like, so let's compare the two words, dog and fog. So as we know, like OG and OG, very similar. Computers love to compare these two words. It's like dog, fog, OG. So this is like a 66% similar, done, right? But if you want to compare the word dog to puppy, I mean, there's no letters similar at all. D-O-G, P-U-P-P-Y, those are not the same. But if you ask a human being, are they similar? The human will say, yeah, they're similar. Like on a scale of 0 to 1, how similar are they? Well, 0.95, right? That's what embedding models can do. You can take a word, compute the vector, compare the two vectors, and you can get a numerical estimation of similar. Those of you who love vectors, it's like a dot product or cosine. It's like you can get the number pretty easily, the similarity of the two vectors. Okay. But what is cooler is you can compare the word dog to my pet when I was a kid. When I was a kid. Okay. So when you do that, comparing dog to my pet as I was a kid, I mean, come on, that's like one word compared to 8 words. The reason why that's possible is because of this translation from semantic space into vector space with an embedding model you call through an endpoint. It converts it into vectors. So let's show you how that happens. Over here, let's go to in workbook 6. What is happening is I'm going to bring my kernel over. And what we're going to do is we're going to build a kernel specifically with, do you see this word here, embedding generation service, text embedding generation service? Notice it's different than a completion service. So I have two models at play right now. What I'm going to do is I'm going to take these strings. My name is Andrea. I currently work as a tourist operator. I currently live in Seattle. I've been living there. There's 5 sentences here, and I'm going to now convert them to embedding space. So I now have 5 vectors. I got 5 vectors now. And what I can do is I can look for similar things. And so let me just run this for here we go. What is my name? Where do I live? What I'm going to do is I'm going to compare the embedding translation of this sentence to all of these sentences, and I'm going to get the most similar sentence. So here we go. What is my name? Matches my name is Andrea. Where do I live? I currently live in Seattle. So what happens is it computed the similarity of this to these 5 sentences, and this is the most similar sentence. Ta-da! Like I can ask like if I didn't even make it like a set question, like a place, a name. Let's see how it does with that. So what it did is place. Notice how it matched place, a place to New York. And notice that a name, it found the sentence, my name is Andrea. Okay, ooh, we're coming to the end of the time. So what I did there is I used the completion model to complete the and then I'm using an embedding model to find the most similar things. So what you can do is you can take all of Harry Potter, you can chop it up into what is like lovingly called chunks. You can stick those chunks all in a vector database. And oh, we can go longer. You can stick all those chunks in a vector database. And what you can do then is you can like use your magnet, the semantic magnet, to pull out all the chunks. And then what you do is you stick them in the completion model input thing you're going to toss over. And what happens is when it answers the question, it answers the question with context. Okay, let's pause for a second to get a key idea across here. I'm going to keep going forward and going backward, going forward, going backward. Okay, so okay. I just claimed something that is a big claim. I claimed that climate. That's good. Yeah, I know. Like, oh, all right, that's good. Let's get going. If you want to stay, if you're gonna go and like take care of something, go ahead. But if you want to stay and watch, we're still going. Here we go. Okay. So okay. So I claimed something that I can take Harry Potter and I can find anything in Harry Potter or ask the Harry Potter book any question by virtue of having two kinds of models. One model is a completion model, complete the sentence, make it taller. There we go. Or I can have an embedding model that does a similarity search. Okay. Actually, this is not good because you can't see. 1 second. Look at I. So we have two models. We have the completion model, complete the and then this one is magically give me something similar. I'm gonna use a magnet here. Everyone knows a magnet. Some people don't know what a magnet is anymore, but a magnet, I can find things that are similar. Similarity engine, association engine, and completion engine, also called generative AI. This one does generative, this one does similarity. These two together are evolving at the same time. If we just had the generation technology, it'd be kind of cool, but we've got the similarity technology too. And it's this combination together that is bewildering us right now, or at least me, because I'm like, whoa, what happened? The two come together because everyone, let's make this symbol here, scissors. So there's someone named Herbert Simon. Herbert Simon was a legend at Carnegie Mellon University. He invented the behavioral economics field, got his Nobel Prize in business economics, but he's a computer science OG of AI. And Herbert Simon had this framing of intelligence as like two blades of a scissors. One blade is cognition, the other blade is context. The two together form what appears like intelligence. And so cognition implying the ability to think. Like think of if any of you have had loved ones who have unfortunately gone through amnesia. I've had an amnesia before. I like hit my head and I like lost my memory for like a few hours. It's pretty scary. But when you have amnesia, you have cognition. This thing is like good, but it's missing memory. Or think of someone who's a little dull. They like know a lot, but they can't like articulate how to work with what they know. So it's this combination of cognition and context. What's important is that this was an idea of intelligence that applies now in 2023, because I think of this model here is the cognitive blade of the scissors. It has this like magical processing power ability that looks and feels a bit like thinking. This thing over here is the context blade. The context blade is able to get context. So let's imagine a world where all we've got is plain old generative AI, Gen AI, right? And like, oh, Van's asking a question. I'm gonna get there. It's good. Okay, I want someone, maybe I'll anoint Lee. Lee, ask me a question. Go ahead, type it in the channel. And Lee, if your fingers are near the keyboard, give me a question in the chat. It can be short. It doesn't have to be like topical. It can be like, what's your name? What is temperature? Okay, now if I'm doing generative AI, I'm gonna say it's 32 degrees Fahrenheit. Oh, I can't spell Fahrenheit. Whoa, bad one. Have a great day. Okay, now that's like a generative AI like making stuff up. Because like I have no idea where Lee is. But I'm gonna like, oh, very good. So Neil's just nailed it right now. I don't have context, but I'm just generative AI. I'm not supposed to be smart. I don't know anything. And so you just sent to the completion model, what is the temperature? And it's going to say, well, of course, it's 30 degrees Fahrenheit. Have a good day. Okay. But as Niels knows, Niels solving this problem is that you don't send that in your token. Okay, so I don't want to give away. Let's say everyone's from Atlanta here. What happens now is that if I say I am in Atlanta in December, that doesn't get 32, so let's just make this up. Global warming is real, but anyways, I am in Atlanta in December. What is the temperature? What is the temperature? So what's happening here is that if you just give Gen AI what is the temperature, it's going to make it up. But if you change the prompt to say I'm in Atlanta in December, it's going to be more likely correct because it's using context. Because the completion engine is like very capable. It's going to do stuff. But if it's missing context, it's nothing. So let's go back to Van's question, which is the great question. And get excited, everyone who's new to this, because this has not been solved as a technical problem. Woohoo, exciting, right? And it's exciting with the frontier. So I've got Harry Potter. Harry Potter, let's say Harry Potter, this book is 500 pages long. Okay, Harry Potter, I don't know which book it is. Maybe my daughters all read them and they were like, I can't read that, it's too thick. 500 pages. So let's say I took all 500 pages and I used that embedding model. I gave it 500 words. Maybe that's too many. Maybe that's enough. 500 words. Let's try that for a second, shall we? Share screen. Let's go over here. Okay, yeah. Okay, so lorem ipsum. You should never use lorem ipsum, I know that, but it's always good. Ipsum, 500 words. Give me 500 words. No. Give me 500 words. 500 words. Give me 500 words. Oh, is that it? 500 words? 500. 500. Okay, I'm gonna grab all these stuff. I'm gonna grab these 500 words, copy clipboard. Okay. And let me go back to Where is my OpenAI 2? Here we go. Okay, that's 1,200 tokens. Ooh, 1,200 tokens. And that's great. That's only 1,200 tokens. And again, it wouldn't be, this is pretty bad. Notice how it's like randomish. So it's probably only 1,000 tokens. I remember I did this one time recently. Okay, so good news. That's pretty good. So I'm going to take 500 pages and I'm going to make a delicious embedding vector for each of them. I'm going to have 500 of them. Okay. Now it's kind of like taking a test, right? Oh, good, Kip. Exactly. I remember hearing when the founders of OpenAI saying the generative needs to replicate, not necessarily provide you an answer. Yeah, well, it's just predicting. It's a very good predictive model. And how do you help a prediction? You give it context, right? So I've got 500 vectors, okay? And that's why there's these things called vector databases now. They're highly efficient ways to manage these long vectors. These vectors can range from like 384 is like a very high speed open source embedding model, the size of the vector. But I think OpenAI's one is like 1,000 plus numbers. And so if you got a lot of these vectors that kind of really add up, and when you do the similarity comparison, you're doing a multiplication, a vector multiplication, which can be time consuming. So the vector databases are being designed to quickly search through databases. Well, we have enough time to like scratch our heads because vector databases are a rabbit hole. Okay, so 500 pages. I've got 500 vectors. Okay, I got 500 vectors in my vector database, and in Semantic Kernel, we have a memory abstraction to stick those vectors into either volatile memory, or you can stick it into a vector database running either in the cloud or locally. Okay. Now, I am now the product lead of the Harry Potter store I recently visited in New York City. Amazing merchandise, mind you. How can they sell so many things? But like now I'm the product manager of a little thing, not as ambitious as my city chatbot, but it's for that just that store, and it's got a little a thing here, and it's like ask Hermione. Ask Hermione. Okay, ask Hermione. So I can ask Hermione stuff. Okay, awesome. So let's say like now if I say what is the most powerful spell you know, Hermione? Okay. What is the most powerful spell you know, Hermione? Okay. Well, what happens is again, if I just ask ChatGPT, or if I just ask the completion model for the answer, assuming it hasn't like read all the Harry Potter novels, what is the most powerful spell you know? It's going to say abracadabra. It's going to make it up. Okay. And that's not going to work in that store because there would be like really angry consumers because Harry Potter is like a religion. I saw a heart mark somewhere, so it's very important. People would like, ban the store. It'd be like terrible. Like no one would visit it. It'd be very bad for business. So the most powerful spell you know, Hermione, the way you do it is let's take this one Harry Potter book. Let's say it's the first Harry Potter book. Right? All you got to do is like I did over there. Let me show you. So like all I got to do is I'm going to go over here and let's open up the window over here. And let's say, let's call this the Harry Potter collection. Again, those of you who I'm not doing anything illegal because I don't know all the stories very well. There's a secret spell that Hermione discovers to change people into stone. Those of you who know it, don't all yell it out at the same time. But it's like Patronus something, whatever. I'm sure. Okay. Let's say that's one string to compare against. The favorite meal of Hermione is definitely mac and cheese. I mean, who doesn't love mac and cheese? Come on, I mean, right? The magic, no, the book that look at this, it knows about the book that is popular in Hogwarts. Hogwarts is a fairy tale. Yeah. Let's give it another one. Well, you know what I'm doing here. So let me just do. I'm gonna take 2 pages of Harry Potter. Again, forgive me for not making this a long story. I'm going to now. I'm going to convert that to embeddings. Again, these 3 pieces of text have gone over to be converted to vectors, and now I'm going to ask for delicious food. Let's try that. I'm going to try that one. I'm going to ask for delicious food. Look, oh my goodness, Hermione's favorite food is mac and cheese. Let's look for powerful magic spell or something like that. It says the secret spell they discovered is change people to stone. Okay. Come on, wasn't that cool? Wasn't that cool? I mean, that is not using generative AI. Thank you, Craig. Thank you. I did not use generative AI. I just use the similarity engine, right? I just use a similarity engine. Okay. So now what I do is with the similarity engine is I grab the chunks that are related to my question, and then I can stick it into a generative AI prompt. You know, it's like and then I can have it finish the sentence. And what happens is it's not a hallucination anymore, because going back to what Niels is saying, it's got context. Okay, got context. Context is truly king, queen, or any kind of non-gendered royalty ruling kind of thing. And they haven't figured that one out yet, have they? And so this idea here of context comes from the similarity engine, the embedding engine, and the other piece comes from the generation engine. Okay, let's go to final stretch now. Now we're going to take that a quantum leap. Let's just make sure that my numbers are not good. Let me make sure I'm abiding by the idea, the exponential. Jason suggested I stay exponential. Oh, question from Ritesh. Ritesh, question, go ahead.
Yeah, I think what you're describing is the RAG pattern, right? So essentially you get the argumentation and correct? Yeah.
Okay. Okay.
But
okay.
yeah, in spite of using the RAG pattern, like getting the vector through the embeddings, we still had problems with hallucination.
Yeah,
right?
It's so good. It's so good. See, we got a ringer here. We got a ringer here. Okay, good. Okay. So before we go over there, let's make sure we stay in this column. Okay. Important acronyms. Everyone, acronyms make you more elite, right? So everyone remembers this acronym. This one and this one. Ooh, they're really good. Okay. RAG stands for Retrieval Augmented Generation. Ooh, good one. ICL equals in context learning. I love these two. They're my favorite. Okay, so Ritesh talks about RAG. RAG, Retrieval Augmented Generation. Let's slow that down for a second. Okay. I'm going to have an embedding model with a vector database, VDB. I've got this. I have a translation of the Harry Potter book. It's living there. I have a generative AI engine over here, a completion engine. Okay. All right. So retrieval, augmented generation. So remember, I have a Hermione's fave spell. Okay. That is my generative posture to finish the sentence. How do I make it hallucinate better? I augment it with retrieval. So I'm going to take Hermione's favorite spell. I'm going to compare it to what's in the database. I'm going to pull out the relevant page. Let's say it's page 12 is where that passage is. And this thing here is a retrieval, augmented generation. Everyone say it with me under mute. Retrieval, augmented generation, RAG. Okay. The other one, in context learning, is somewhat similar, but you should look it up. But it's an example of in context learning is so-called few shot, multi-shot. But it sort of rhymes. But again, important work. And what Ritesh brought up is that there are cases where, okay, I pulled page 12 and Hermione's favorite spell. It turns out that on page 12, it has something, it isn't the best page. It's something random going off about, and then there was a time that Hermione's mother had cast a spell and turned, the son of her brother into a frog and blah, 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 blah. So what happens is it pulled the wrong chunk. And so now it's going to complete the sentence. Think of when you're going to, if you remember taking tests, those of you who are near the era when you took a lot of tests, and there was the teacher says, this is a test where you can bring in a cheat sheet. So imagine bringing a cheat sheet into Hermione the Muggle dude. See, this is stuff I don't know. I'm sorry, I just don't know that magic. Okay, there's it. Harry Potter, bad metaphor to use. But page 12 is wrong. You brought into your test the wrong fact. And what are you going to do? You're going to hallucinate too, because you have the wrong context. So what is very exciting today is the science of getting the right context. And so since Ritesh asked for an advanced recipe here, one of the ways to be able to to augment your retrieval better is amazing. So let me describe two strategies for reducing the possibility of your retrieval being more. Again, the hallucinatory word just means error. Remember syntax error? I wish people called it an error, but it's hallucination sounds much more exotic. Okay, so method number one. It is called using your chunking strategy different. So let's say I have 500 pages. I have 500 pages. My very simplistic way of doing that was making 500 vectors. 500 vectors, right? But a page is a pretty big quanta. So what I can do instead is I can break the page into half. I could break it into quarters. I can break them into individual sentences. I can break them in all kind of places. This is the so-called chunking strategy. Chunking strategy. And now that you think about that, they're like, well, what if you pulled the wrong chunk at the wrong border? Exactly. So there are people who describe chunking strategies where, let's say this is the page. And let me get a right marker. You might grab this chunk and then you do chunk overlapping. You see that? Chunk overlapping? It's like overlap chunk. So it's like you don't want to lose the context. Okay. This method of trying to get the right chunk, it's a purely chunking strategy base. And since Ritesh has asked this question, Ritesh already knows the answer. There's many ways to do this, but let me give you the second way that is emerging as a popular way. The second way, if I get this camera working, the second way is to summarize chunks. To create a hierarchical chunk. This chunk word evokes bad things. So you can build a hierarchical set of summaries. Let's say you took Harry Potter, that book, and you can summarize the entire book at the top note. let's say it was, and again, you Harry Potter people like know how many chapters are in this book. Let me say there were just 5 chapters, which is impossible, but let's say there's 5 chapters in Harry Potter book. It'll have 5 little summaries. And then let's say it's broken into subsections, and then each subsection is summarized. You see that? So this is a clever way to hierarchically burrow down into the right chunk. But what is the problem? No problem. To do this, though, you're going to use the model, the generative AI model, to produce each chunk. So each of these summaries, 1, 2, 3, 4, 5, whatever, you're going to be able to pay. You're going to have to pay tokens to do this hierarchical summarization of chunks. Are you with me? This is like new territory. There's other ways to chunk. There's keywords, sort of like clustering. Anyways, thank you, Jason. It's lossy, 100%. So I would just say that what's so exciting about this era is that this context piece is a technically unsolved problem. However, going to what Ritesh has probably done in their work is the following. Let's think. So that I gave you 2 ways to reduce hallucinate. Well, technically speaking, make it more correct versus 100% correct. I think the most important thing to consider is I wouldn't even call it a similar model. It's the following. Step A, make sure that your vectors are organized in some way more than just like chunks of pages. And then number 2, make sure your query it matches the structure. So what does that mean? So another way of being able to break that Harry Potter up is to extract the different keywords or hierarchical patterns or clusters of Harry Potter plot points, and to be able to break them out into clusters and subclusters that are topical. Again, this requires more token usage on the Gen AI side. And then when you're asking the question, like, what is Hermione's favorite spell? You use the model to change this query into, what are the keywords out of these N keywords are we looking for? See that? It's like you're shaping the database with Gen AI, and you're reshaping the query with Gen AI to find following that. Yeah, this is an amazing era. Okay, so and with Ritesh, go ahead.
Yeah, so in summary, what I should be doing is I should not be just chunking based on a page. Rather, I use Gen AI to help with chunking.
Yeah.
And also,
Great.
The second part, I think what you describe is essentially improve my own prompt with Gen AI.
Yeah. Isn't it
Okay.
neat? It's like mind blowing.
Right.
And it makes sense when you think about it. And because we're trying to, that phrase in the US Constitution, a more perfect union. We're trying to make a more perfect union when we're working with this stuff. But before we go, very important. I want you to look at in the workbook. There is a piece on planner. And the planner is the most interesting piece of semantic kernel, I believe, which enables how to describe it. So let's say here I'm going to build a kernel. I'm going to set up a planner, and this is my workbook. I'm messily hitting random things, so that's like I'm not going to. Now what I'm going to do is I'm going to register different skills, plugins to summarize and to write. I'm going to say tomorrow's Valentine's Day. I need to come up with a few date ideas. My significant other likes poems, so write them in form of poem. I'm giving a very high level prompt, And what the planner does, it dissects the high-level ask into sub steps, and it's able to pick the certain AI skill to use. Here it's saying it's pulling out the ability to brainstorm. It's pulling out the ability to write a short poem. And it's sort of built a plan. So let me show you here. I'm going to, let's do this. So tomorrow's Valentine's Day. I need to come up with a few date ideas. She likes Shakespeare, so write using his style, write them in the form of poem. I gave this ask, the planner, different AI functions to be able to do stuff. It builds the JSON plan, and then what happens is I can run it. And when I run the plan, what happens is it basically figures out from my high-level ask which AI functions to use. And this is a sample of that. And then if you look at the last one, it's going to basically create a plan for the date, all expressed as poems. A picnic in the park. Oh, what a delight. We spread out our blanket. Everything is just right. And step 2, moving at home, cozy and warm. Recycle. Does it have notice how it ran out of tokens, so they add more tokens? What that means is that the vocabulary I'm showing you leads to the ability to do what's called agent-like behaviors, agentic behaviors that are multi-step plan-based, automatically generated high-level sequences of code, whether native or semantic, which means that a lot of times we write like subroutines. What happens in this new era is that we give AI tools to work with, plugins, and then what it does, you can give an ask. Gen AI looks at what plugins are available, can sequence them, and it can do them step by step. If you let it execute that. That's why people are really curious about this different model of programming, where we build the components, we work with the plans, have the AI generate the plans, and we're finding more and more people want to store those plans and play them back. So it isn't like writing programs. I think in the beginning of the call, I heard people talking about how I can write code. It's more like you can help to execute high-level plan-based behavior, which is above the layer of algorithms per se, but jobs to be done. The jobs to be done, humans want to be at the job level versus the algorithm level, and that's kind of new. And so if you make AI plugins, you can run these AI plans, and Semantic Kernel is a way to kind of help you see there. So that's it. I think we covered as much as possible. Custom Copilot recipe. We have a repo called Semantic Kernel Chat Copilot. It's got a full-fledged sort of cool Tesla-like Chat Copilot running. JavaScript front end, .NET back end. I talked about different difference between Azure OAS SDK. It's more low level. Ours is sort of mid-level, aiming high. If you're a 30-year coder, this is 30-year coder. This is the best time ever to code. So thank you for coding, because we need your expertise. What the heck's the Copilot stack? There's a great talk on the Build site for 2023 that Sam Scalace, myself, and my colleague Tim Laverty goes over that. All right, on time. Oh, 5:30. I got to go feed my mom. I take care of my 80-year-old mom, so I got to go. She's 88 now, still alive. She always says she's still alive. Okay, any last needed? Ritesh, yeah.
Yeah, one last question. So
yeah, go with it.
Yeah, I've only played with OpenAI, and I'm curious if the other LLMs like the Eagle and Bard, they have the same concept like prompts and temperature and tokens. Are they hallucination? I mean, do we have everything similar going on in the other LLMs as well?
I gotta say that, people are asking what's the differentiation between all these models, whether the closed source ones or the open source ones. I'm just gonna say that the Microsoft sort of Copilot stack is designed for safety. It's designed to protect data for the corporation that uses it. It's very enterprisey. So I tell people that well, the stuff we do smells very enterprisey. And I volunteer the fact that it's for the boring, reliable thing that you'll do with AI. And in general, all this stuff does the same thing. The question is how much of a kind of commitment to responsible AI there is. And I think everyone's trying to be responsible too. But as far as I can tell, Microsoft is very focused on that. That's why I'm proud to work here. Good. I'm glad it was useful to some of you. There's all kind of levels in this group here. Okay. All right. I'm gonna go feed my mom, make something for her.